1, 0.
Uno, dos, tres, cuatro.
Hi everyone, today's the start of our polynomials chapter for Pre-Calc 12. We do polynomials almost every year in math and BC here, and so a lot of this is going to be review, but this chapter we're going to start taking a look at how to graph some polynomials that are beyond just a linear and quadratic function, and that's the real exciting part for Pre-Calc 12 as opposed to some of the previous years. So what do you call a parrot who won't eat? Polynomial. All right. Okay. All right. So polynomials. In terms of trying to find out a definition, I think the best way to do this is start to actually like work through some of these questions. And we'll define things based off of what we can see, some of our restrictions and what are in terms of what we have. So let's begin by looking at a couple examples of polynomials that we have right here. And a couple review terms that we usually write it in a descending degree order. So you would say, here's x squared followed by x followed by your constant value in this example being 4. But your leading coefficient, your front number that's in front of your variable of x squared is a 3. So in this case, the leading coefficient there is 3. And it's a second degree polynomial because 2 is the highest power that we have in that example right there. If you wanted to look at some differences between what makes something polynomial versus not polynomial, a graph of a polynomial needs to be smooth, continuous, and you're going to start to see some different shapes that it could possibly take on. But here's some examples of what some polynomials are. So for a polynomial function, we know that we're going to have some sort of y value or f of x value in front of it to make it a function rather than just an expression. This would be a cubic function. Here we just have 3x, so that's actually a linear function. And here we have something that's to the power of 5, which we're going to name in about 2 minutes from now. So this right here is something that would look unfamiliar to us, but it is something that is going to fall in our definition of a polynomial. The example on the right of the graph, that's some form of a rational function, and we've learned rational functions in Pre-Calc 11 and in Pre-Calc 12, and we know that that's not going to be something that would have the characteristics of what makes a polynomial. So in each of these, let's identify the bad parts of our function that makes it not a polynomial. So here you have something in which you have something where x is raised to the power of -2. So the first thing that we can start to say is that the exponent has to be something where it's going to be a whole number. So something like a 3, a 2, a 1, a 0, but you couldn't have something where your variable is raised to the power of something that's going to be a negative number or any sort of decimal number or fraction number. It's got to be a whole number. So right here, let's make a little note and let's just say that we want our exponent to be a whole number. And when we think of a whole number, we know whole numbers start with 0, 1, 2, 3, so on. Okay, and a good way of remembering that is it starts with a 0 because 0 looks like a whole. 1 over x, that's the same as saying x to the power of -1. So we know that's not good because that would not be a whole number. So that is not a polynomial function. 2/3 as an exponent, that's not a whole number. So that's why that's not a polynomial function. And the square root of x is the same as saying x to the power of 1/2. So that would not be a whole number either. Take a look at what you have in terms of the coefficients. And if you take a look at the coefficients, now for some of these examples, let's actually look right here. Here's the root 2 for something that falls in line with a polynomial function. Your coefficients are allowed to be any real number. And the square root of 2 might sound like something that could have something that's off, but you're allowed to have a coefficient is any real number. Okay. So here's the real nuts and bolts of what we're going to get into. So we've learned in grade 10 about linear functions. In grade 11, we learned about quadratic functions. And now we're going to look at what's going to happen if you have something where you have x to the power of 3, x to the power of 4, and x to the power of 5. So you'll have a cubic function, a quartic function, and a quintic function. Okay, so this is intended to just give us an idea of what some graphs can look like through sketches. A positive leading coefficient means that your front number is going to be something that's positive. So it could be something like 2x plus 3 or something like that. That would be an example of a linear function of degree 1. And if you're to do a sketch of that, it would look something like that. And if you have a linear function, we'll talk about the number of zeros for minimum and maximum zeros coming up after we've summarized a few of these other ones. So quadratic function, again, don't worry too much about these details, but you could say something like x squared plus 7x plus 10 and make some sort of a parabola. And I know that the sketch here isn't going to necessarily match up with what our function is, but we have a parabola. And because we had something that was positive, then we know the parabola opens up and it smiles. So some books and some other teachers may talk about hills and valleys. What we're going to talk about is for the linear function, this was basically like one continuous piece. And then for the quadratic function, you had a minimum point. So it was like 1 and then 2 pieces. So for a cubic function is going to be 3 pieces. 1, 2, 3. Okay, and if it's a positive cubic function, its end behavior, its arrows are going to resemble the same end behavior as a linear function. You're going to have something in which you terminate in quadrant 1 and quadrant 3. Not terminate, but it extends through quadrant 1 and quadrant 3. So an example of a cubic function could be x cubed plus 2x squared minus 7. A quartic function. Well, a quartic function is an even degree, 4. So it's going to resemble something that's going to look more like our quadratic function, which was also an even degree of x squared. And if you notice that if that pointed upwards when it was positive, then we're going to need to have 4 pieces, and it's going to have to be positive. So it's going to make something that looks like the letter W. There's 4 pieces to it, and our arrows point up because it's positive. And so remember we said you could have any sort of coefficient. So we could say here's like 1/2 x to the 4, any real number, minus x cubed plus 3x plus 1. And then a quintic function, I bet you could probably make a pretty good prediction on what this quintic function is going to look like. It's going to resemble x to the 1, x to the 3, x to the 5. So its end behavior is going to go in quadrant 1 and quadrant 3. And so it's going to look something like 1, 2, 3, 4, 5. Okay. And let's do something stranger. Let's say the square root of 3, x to the 5. Notice the square root doesn't extend over the x to the 5. Just it's the coefficient in front of it. 3x to the 4 minus x. We'll just leave it at that. Okay, so now let's look at the zeros, the minimum number of zeros and the maximum number of zeros. And so if you take a look at something like this, for a linear function where you have xer and yer, at some point, no matter what, it will always cross the x-axis. As long as it's x to the power of 1, you're going to have something where that happens. So the minimum number of zeros you have is 1, but the maximum number of zeros you have is also 1. Okay, zeros, remember, meaning are x-intercepts. Now for a quadratic, if you have something like that, you could have a quadratic like we have right here that has 2 zeros, but what if you had a quadratic that started above the x-axis? You could have 0 zeros. So our values change a little bit. If you have a cubic function, your maximum is going to be 3, and you'll probably start to notice the pattern now that the maximum number of zeros is the same as the degree of the polynomial function. So we can actually fill in, this would be a 4, and this would be a 5. But our minimum number of zeros, well, for an odd degree, let's think about this. You could have something in which you went like that. That would still be our 3 pieces, but you only crossed once, but at some point you're going to have to cross. So for a quartic function, you could have a quartic function that is fully above the x-axis, and it could have 0. And then for a quintic function, it has to have 1. So you could come up with the generalization now that's saying for an odd degree polynomial, you're going to have a minimum of 1 0, and for an even degree polynomial, you're going to have to, you could have a minimum of 0 zeros or 0 x-intercepts. So a quintic function could be anything potentially like that. Okay, so each of those were positive leading coefficients. If you have a negative leading coefficient, we're going to whip through this pretty quickly. The first thing is that means that you would have a negative linear relationship. A parabola would open down. A negative cubic function would be something in which it would now be in quadrant 2 and quadrant 4 for its end behavior, so it could look like that. A negative 4th degree function, you could probably predict, and it's going to resemble the letter M. And a 5th degree would be something like that. 1, 2, 3, 4, 5. Okay, the 0 behavior is going to be exactly the same as what we had for the positive coefficients. It means that the maximum number of zeros continues to be whatever the degree of the polynomial is. So 1, 2, 3, 4, and 5. And then whether it's odd or even is going to depend on the number of zeros. So here we could say that's odd, even, odd, even, odd. Okay, and if you want an example of each of those, we can give an example. We'll do this really quickly. Y equals negative x plus 3. Y equals negative x squared, minus 2x plus 6. And if you're saying, how could that have no zeros? Well, you could start below the x-axis and then just end by pointing down. If you have a cubic function, that could be something like y equals negative 2x cubed plus 3x plus 1, negative x to the 4 plus 2x squared plus 3x minus 1. And how about this negative, let's go negative 5x to the 5, crazy, plus 3x to the 4 minus 2x plus 3. Okay, so hopefully just that intro makes sense. As we move on now, here's a good way of just seeing if we understand what's going on. What degree polynomial do we have right here? Okay, so take a minute, think about it, and hopefully you would say that is 1, 2, 3, 4, 5. That's a 6 degree polynomial. Okay, just a quick review. Quadrants, quadrant 1, 2, 3, 4. Having just finished transformations, I'm sure you're an expert on that. Okay, in terms of end behavior, I'll let you pause this if you want to go through that, but that basically summarizes what happens if you have an odd degree versus if you have an even degree. And end behavior will become more important as you start to do some calc, but it's just going to talk about what happens for extreme values as x approaches infinity or as x approaches negative infinity. Okay, example 1, find the y-intercept of the following polynomial functions and describe the end behavior. So the y-intercept, remember, you can find by making x equals 0. And in each of these examples, if we make x 0, there we get negative 2. And here, if we make x 0, we could actually just times the back values by each other. Negative 1 times 4 times negative 3 is going to give us positive 12. And for the end behavior, now again, you could graph this. You could put in your graphic calculator. You could use Desmos, but we know that this would be a negative cubic function, and a negative cubic function had something where you terminated, or not terminated, but you extended to quadrant 2 and quadrant 4. So depending on how you want to write this, we can just describe it. You could say something along the lines as x values get very small, so as they go to the left forever, the y values get very large. So you could say something like as x gets smaller, y gets larger. It's probably not the best description, but that's describing what's happening. And then over here, as x approaches positive infinity and goes to the right, you could say as x, as x gets larger, y gets smaller, points down. Okay, now for this next example here for part B, we have a positive cubic function. Again, this is just a sketch. It's not exactly describing what that is, but we know that that is a positive cubic function. So you could say here as x gets smaller, so as x goes to the left, as your values continue to go to the left for x, your y values continue to point down. So you could say y gets smaller. And as x gets larger, y gets larger. Okay, so what happens here where we have to now figure out the zeros and the end behavior. So it looks like we have a negative quartic function. And if we don't know what the zeros are right now, we can easily find them out by factoring. So what you could do is you could say, let's factor out, in this case, let's factor out what would happen if we factored out a negative 3x squared. We'd be left with x squared minus 1. And then that would tell us that it could become y equals negative 3x squared, x plus 1, x minus 1, which means that the zeros would be at negative 1, positive 1, and if you have just an x squared in front, that means that you have something at 0, and it's happening twice. We're actually going to learn this number, or what this term is called, really soon, but it's called x equals 0, and in that case it has a multiplicity of 2. And what that means is, because it says x squared, it's equaling 0 2 times there, so we express that by saying it has a multiplicity of 2. That's a negative quartic function, so a negative quartic function in general looks like the letter M. And so if they want us to describe the end behavior, then we could say as x gets larger, actually let's be consistent, as x gets smaller, y gets smaller, and as x gets larger, y gets smaller. Okay. Here's a note on the summary of zeros, so x-intercepts, and we've actually learned that from before in our previous sketches, so I think we're okay with there, but you can take a look at that note and hopefully that makes sense. Multiplicity, we just briefly explained it, but basically multiplicity says that when you have a solution that happens more than once, especially, so if it's repeated, in this case they're saying r times, it's said to have a multiplicity of r. And so we'll do a couple examples where they're going to ask for its multiplicity. Okay, example 4. Find the zeros and multiplicity of the polynomial function. Okay, so right here we would have x minus 1, x minus 1. So we have zeros 1 and 1. And here we would have zeros -1, -1, -1. That's happening 3 times. So if you want to list the zeros, you could write them out like that. Or you could say x equals 1 with a multiplicity of 2. And here you could say x equals -1 with a multiplicity of 3. It's kind of a different way of doing that. So why don't you pause the video right now and see if you can factor part B appropriately and then find the zeros and the multiplicity. Okay, so right here it looks like we could factor out an x squared. We'd be left with x squared plus x minus 6, and inside that brackets that is factorable as well. And so you would end up with something in which you could say, well, I get the solutions of 0, 0, -3, and 2, but instead of listing that out, I could say x equals 0 with a multiplicity of 2. This is kind of a silly point, but you could say x equals 3 with a multiplicity of 1. It's kind of unnecessary in my mind, and x equals 2 with a multiplicity of 1. Okay, so we probably overemphasized how important it is to talk about multiplicity, but hopefully that's clear. It's just saying the number of times that solution occurs. Okay, so based off of that, you got a few questions to be able to practice from section 3.1, and that's an introduction to polynomials.